Thank you, everyone, for joining us today for this seminar. And we are delighted to introduce Patrick Jardine, who will be sharing his insightful research on field experiments investigating snowpack compactions as a method for lowering ground temperature. And Patrick is currently pursuing a master's in physical geography at Carleton University under the expert guidance of Dr. Chris Byrne. His research is centered around enhancing infrastructure sustainability and longevity in permafrost regions. In 2019, Patrick completed his bachelor's degree in physical geography with a minor in earth science, where he demonstrated a strong commitment to academic excellence. His dedication was recognized through the receipt of an NSERC undergraduate research award for his study on pollution levels in Ottawa-Rideau River system. For his master's research, Patrick embarked on extensive field work along the Dempster Highway in the Yukon Territories, with a specific focus on exploring snow management techniques to minimize the risk of infrastructure damage. Throughout the winter months, he traveled to various field sites in central Yukon, meticulously collecting data and closely observing the impact of snow compaction on ground temperature. And today he will be sharing his experience and findings regarding snow management techniques with us. Patrick, we sincerely appreciate your presence here, and we are excited to hear about your research and looking forward to your presentation. Please feel free to begin whenever you are ready.
Great, thanks, Zakia. So yeah, my project was compacting snowbanks to lower ground temperatures and observe permafrost. First, I'll talk about some background research on how snow can influence ground temperatures and damage highway embankments. Next, I'll show the results of my field experiments and talk about what effects compaction had. And then finally, I'll provide some existing research into snow compaction to control ground temperatures and discuss the viability of the technique and areas for future research. So first off, the problem with snow accumulating beside embankments is that snow is a strong insulator, making it trap heat within the ground. Because the snow is cleared from the driving surface onto the shoulder, it creates a surface energy imbalance that causes the ground underneath the shoulder to warm up. On the Dempster Highway, temperatures were measured as being about 1 to 4 degrees higher underneath the shoulder compared to the center line because of this process. This was kind of Stockton in 2019. If the permafrost begins to thaw, this area is going to thaw first, causing embankment shoulders to lose support and putting strain on the driving surface. This is shown in the diagram in the top right. If there's enough strain, then the driving surface will fail, either by cracking or shoulder rotation in severe cases. That's pictured in the bottom right, and it looks like a really big headache to clean up. So compacting the snow is intended to increase its thermal conductivity so that heat can escape more easily and the risk of road damage is reduced. Describe how snow affects permafrost temperatures. It can be broken down using the TTOP model. DDTA and DDFA are the thawing and freezing degree days for each season. To calculate degree days, you just add up the mean daily temperatures in degrees Celsius for each day. And T and NF are the thawing and freezing end factors. These are calculated by finding the ratio between ground temperatures and air temperatures. The thawing end factor is usually less than 1, so the ground is cooler than the air because of shade and evapotranspiration from vegetation. The freezing end factor is also usually below 1, so the ground is warmer than the air because of insulation from snow. Together, the vegetative and snow or nidal offsets make up the overall surface offset, which determines mean annual ground surface temperatures relative to air temperatures. Going below the surface, RK represents the ratio between the thermal conductivity of the active layer during the winter compared to the summer. These are different because ice has 4 times higher thermal conductivity than water. This difference causes a thermal offset, which is cooling that happens through the active layer until you reach permafrost. where the DDF term on the right of the TTOP model is larger than the DDT term on the left, you have permafrost. Compaction is intended to increase the DDF term by making NF larger, so ground temperatures are more closely coupled with air temperatures during the winter. So far, I've been talking about snow as if it's only a single solid substance, and the only factor at play is the thermal insulation it provides. But in reality, a snowpack is a dynamic and layered mix of air, water, and ice, and it impacts each component of the surface energy balance in some way. At the snow surface, the high albedo of snow causes it to reflect most shortwave radiation. The snow also has a high emissivity, so it emits lots of long-wave radiation, and usually this combination lowers ground temperatures at the snow surface. But because of Kirchhoff's law of thermal radiation, the snow also absorbs more long-wave radiation. This means that on cloudy days, when there's lots of downwelling long-wave radiation, the snow might instead experience surface warming. In terms of sensible heat, the snow smooths the ground surface, reducing air turbulence, so less heat is transferred through advection. Small amounts of sensible heat are also transferred through moving air within the snow. The latent heat flux is modified by evaporation and condensation of the snow surface, but also by phase change within the snow. This can happen on a large scale if there's a temperature gradient through the snowpack with moisture available. In this case, snow near the ground can warm up and undergo sublimation, which absorbs heat in the process, before the water vapor then flows upwards and recrystallizes once it reaches lower temperatures, releasing the heat higher up. Over time, this process can metamorphize the snow into a new form called depth warp. The low thermal conductivity of snow usually dominates its influence on ground temperatures, but it's important to keep in mind the other components of the energy balance because they're all modified by compaction in some way. Compaction increases conductivity of the snow, but permeability is also reduced, which limits airflow, and the snow surface will also be chewed up by compaction, so the radiative cooling effect might be reduced. The biggest effects the compaction has on the snowbank are to increase its density and reduce its depth. Both of these changes will increase thermal conductivity. The increase from reducing snow depths happens because there's less distance that heat has to travel through the snow to escape into the atmosphere. This relation isn't linear though, as thermal conductivity usually starts to level off at about 40 to 50 centimeters of depth. So changes above that might not be as impactful. When the snow is shallow, usually up to about 10 or 20 centimeters, then the radiative cooling from the snow surface might be enough to outweigh the warming from insulation and cause the snow to instead cool the ground. For snow density, on the right is a diagram showing its relation with thermal conductivity. As density increases, the amount of air trapped in the snow is reduced, and because air has 90 times lower thermal conductivity than ice, this causes the overall thermal conductivity of the snow to go up. The reason the diagram on the right is so scattered is because the thermal conductivity of the snow is really a product of its grain size, skeletal bonding, and temperature, but snow density offers a simple and easy proxy for these properties, even if it's imprecise. And you can make note of the tiny little triangles right at the bottom of the thermal conductivity. Even at higher densities, they retain that. That's depth Thor, and that'll be relevant later on. So important to just make note of that. Now, some of the background is out of the way. With that in mind, here were the objectives of my field experiments. First, I wanted to test the effectiveness of the technique in general, so whether the force of compaction was strong enough to significantly change the depth and density of the snow, and whether this would actually reduce ground temperatures. Then I wanted to test how the technique works in different snow conditions, mainly soft and hard snow. Finally, I wanted to test how it affects the treatment results if you vary the timing and frequency of compaction. Although the timing aspect kind of got messed up because I was mostly interested in compacting the snow early to speed up freeze back. But because of delays from COVID, I only arrived at sites at the end of November when there's already deep snow and the ground is frozen. So the early compaction wasn't all that early, but I still tried it. These are the sites I selected for the experiments. On the Dempster Highway, I was shown around by Fabrice Kelmels and Louis-Philippe Bois from Carleton University, who helped find a long straight stretch of flat road, about 600 meters, that had mostly low-lying vegetation. Here I set up 10 field plots, all on the same side, so they'd have the same wind conditions. And these were interrupted by 2 empty plots containing culverts I wanted to avoid. Half the plots were left undisturbed, and those are labeled DU and this satellite image up top. The other half were compacted, and those were labeled DC. Over the 5 months left in the winter, DC1 was compacted monthly, 2 bi-monthly, 3 only once in the middle of the winter, 4 early, so 3 times during the first half, and DC5 was compacted late, so 3 times in the second half of the winter. In Mayo, I explored the area around the village with Nacho Nacta and land guardians, including Blaine Peters, Lawrence David McLaren, and Gary Hope. I settled on 4 spots. M1 was located coming into the village from the Klondike Highway, and it experienced heavy traffic in general than the other sites. M2 was in swampy terrain with stunted trees, suggesting there's permafrost in the area. M3 was on a less trafficked mining access road surrounded by thick forest. And M4 was about 3 kilometers down the same road in an area where the forest had recently been burned. So see if that would make a difference in wind and snow conditions. All of the Mayo sites had recently had matching undisturbed and compacted plots, and the plots were compacted every month here, unlike the Dempster site. At the Dempster Highway, the high wind speeds above tree line packed the snow into dense slabs, whereas around Mayo, wind speeds were slow, so the snow was able to accumulate into softer layers. For climate, the Dempster Highway sites were at 1,100 meter elevation in the tundra, just above tree line. The mean annual temperature was negative 6.7 degrees at kilometer 124, which was about the same elevation as the kilometer 97 site, so it's likely very similar. Mean annual precipitation was 466 millimeters at Klondike Maintenance Camp near kilometer 65. The site was 150 meters higher up in the mountains, so precipitation was likely a little higher there. In Mayo, mean annual air temperatures were about negative 2.1 at the airport, with 300 millimeters of precipitation. And this was not too far from the site, so it's likely pretty similar. Both sites had high temperature variation due to their continental climates, and this created a strong temperature gradient through the snowpack that was ideal for depth ore development from temperature gradient metamorphism. All plots set up around Mayo and on the Dempster were 50 meters by 5 meters, marked using wooden stakes beside the road. And here I've repeated the compaction schedule throughout the Dempster. Compaction was done by members of the Nacho Nacta using snow machines. They drove over the sites repeatedly until any more runs no longer made any noticeable difference in the snow, and this would usually only take a few minutes. Each site had a temperature logger buried in the middle at the base of the snowpack, and after the snow was compacted, snow depth was measured along the plots, and snow pits were dug to measure the hardness, density, grain size, and shape in each layer of snow within the pits. These graphs show the mean snow depths from 4 measurements taken every 10 meter along the lengths of the study plots following compaction each month. The red circles show the compacted plots, while the white circles show the undisturbed plots. At the Dempster sites, the circles are white during the months the plots weren't compacted. I've left out DC5 partially because there wasn't much room for it, and partially because snow conditions were a bit different there. The plot was only compacted starting in February, but snow depths were already significantly deeper at the undisturbed plot right from the beginning of the winter. That was because the plots were located right at the end of the field site near a swampy depression that the snow was flowing into. But all the other sites were mostly pretty fine as expected. Because the Dempster sites were in tundra, the snow was hard enough to walk on, and measurements were taken from the center of the plots. At the Mayo sites, the snow was too soft, so measurements were taken by leaning over the edge from the embankment to minimize disturbance. The Dempster Highway, both sets of plots began at about 50 centimeters snow depth, but the compacted plots only rose to about 70 centimeters over the course of the winter, while the undisturbed plots rose to about 80 to 100 centimeters. Overall, over the course of the winter, the mean snow depth of the undisturbed plots was 71 centimeters, while at the compacted plots, it was 62. In Mayo, the snow also began at about 50 centimeters, but compaction immediately lowered the depth to about 20, and the difference in snow depth persisted throughout the winter. The mean snow depth of the undisturbed plots was 71, the same as at the Dempster Highway, but the mean depth of the compacted plots was only 40 centimeters. So compaction was generally more effective in Mayo, but in D1, which was the only plot that was actually compacted each month, there were comparable differences in snow depths, so it's not entirely clear. These plots show the weighted average hardness and density at the field plots. Hardness was measured for each snow layer using a semi-quantitative scale, where 0 indicated the snow could be penetrated by a closed fist, 1 is 4 fingers, 2 is 1 finger, 3 is a pencil, 4 is a knife, and 5 means it can't even be penetrated by a knife. Density was measured by collecting 100 milliliter samples of snow and weighing them using a spring scale. Properties were multiplied by the proportion of the snow pit that the layer they were measured in took up, and then all the layers were added together. The blue circles show the undisturbed sites, while the red are compacted, and the month the snow pit was dug is indicated beside the circles. In Mayo, the natural snowpack consistently had a density of about 150 to 200 kilograms per cubic meter, and hardness is near 0 or 1. After compaction, the hardness rose to about 3, while the density rose to about 350. At the Dempster, natural snow conditions were harder and more dense, and with greater variance. Generally, the snow had a hardness of about 2 and an average density of about 270 kilograms per cubic meter before compaction. And after compaction, the average hardness rose to about 3 and the density rose to about 311 kilograms per cubic meter on average. Even though the initial snow conditions were very different, after compaction, the snowpack physical properties were pretty similar. These graphs show the structure of the snowpack based on how commonly each type of snow was found within them. The graph shows the average snow composition from all 5 snow pits dug at each plot over the winter. The 5 types of snow included are dendritic, or fresh snow that's retained its shape, moderately rounded snow that's undergone some mild weathering, well-rounded snow, snow with some angular facets, which is snow that's been partially metamorphized into depth ore, and then the depth ore itself. The snow types are positioned where they're most commonly found throughout the snowpack, but any snow type could at least sometimes be found at any depth. The dendritic snow and depth ore are the softest snow types at both locations, and this made them the most susceptible to compaction. In Mayo, every snow type had less accumulation at the compacted plots, except well-rounded snow, which increased in thickness. The dendritic snow layer was mixed in with surrounding snow, so there's almost nothing left. And there's also no more depth ore at the compacted plots after the first month. The reason there's some red there is just because the first month's impacting the average. At the Dempster sites, the only other snow type with significant reduction at the compacted plots was depth ore, while there was an increase in well-rounded snow. So back to some theory for a moment. Here I'm going to try to explain how compaction is physically affecting the snowpack based on these results. The compressive strength of snow increases exponentially with its density, and this is shown in a diagram on the right. On the x-axis, I've added the average density of each snow type on the Dempster Highway. On the y-axis, I've estimated the pressure exerted from the snow machine based on napkin mass. Google told me an average snow machine weighs about 500 pounds, and I assumed a 160-pound rider, so I could convert it to a nice even 300 kilograms. For the snowmobile tread dimensions, I looked up dotalk.com forums, and some user revealed that 137-inch long, 16-inch tread comes into contact with 44 inches length of ground surface. So 44 inches times 16 inches equals 704 square inches, which was converted to 0.454 square meters. And I rounded that up to 0.5 square meters to account for the surface area of the skis and because it's easier. 300 kilograms over 0.5 square meters comes out to 0.06 bars of pressure, or 6 kilopascals if you want to use normal units. Based on this pressure, the density of snow that can withstand compaction is just over 0.2 grams per cubic centimeter. Depth for falls comfortably under this, which explains why it was the most reduced by compaction, while dendritic snow is on the fringe. And just to be clear, this is the failure point of the snow. So if it's above this point, it will still increase in density and hardness. But this is when you put it under press and it gets smushed. This is the weight where that happens. I didn't include the Mayo sites on this graph, because snow types on this graph, because they're very homogeneous and they all averaged about 0.18, except the dendritic snow, which was 0.14. So that puts all the different snow types in the smushing range, which explains why there was depth reduction throughout the snowpack. The bottom diagram shows how snow reacts and recovers from pressure. The ice skeleton partially breaks and partially bends, with the bending part recovering once the pressure is removed. This explains why repeated compactions didn't always translate into equally large difference in snow conditions. The first compaction will crush the weakest bonds, and subsequent compactions will progressively less effect. Once the snow grains are pushed into closer contact by compaction, it promotes sintering, which was a form of equitemperature metamorphism that conjoins the snow grains together. This process can create further increases in density over time, even after the pressure of compaction is ended. Now back to the data. The first thing you might notice is that M1 and M2 are missing, and might be a bit confused by that. And I was also confused when I showed up to my M1 field site in spring and the logger was completely missing, and at the M2 site when it was completely flooded and not working. Those were the first sites I checked, so that was pretty scary, but fortunately every other logger was fine, and we were able to see the results from those. So from these loggers, we can see a surprising trend. Even though compaction created a much larger change in snow physical properties at the Mayo sites, the temperature changes at the ground surface were pretty similar. It's difficult to compare between sites, especially considering the Dempster plots mostly had different compaction schedules, but it's fair to say the compaction was effective at reducing mean daily ground surface temperatures by about 2 to 3 degrees Celsius on average at both locations, even though most of the snow at the Dempster Highway was resistant to its effects. Early in the winter, when air temperatures were relatively warm and often swung near 0 degrees, temperatures of the compacted and undisturbed plots were mostly coupled together. In the second half of January, a sustained cold spurt hit, and mean daily temperatures quickly dropped to below -35 in Mayo and below -40 at the Dempster. This caused temperatures of the compacted and undisturbed plots to diverge, with the greatest differences in temperature between the plots being recorded in February, and that was 9.6 degrees at D1 for the Dempster plots and 12.1 degrees at M3 for the Mayo plots. After this cold spurt, the difference in temperatures was reduced and stayed mostly steady at about 4 or 5 degrees until the thawing season. Looking at the timing and frequency of compaction, DC1 had the lowest average and minimum temperatures of the Dempster plots, and that suggests that repeated compaction did have some benefit. DC3 was initially closely coupled with DU3, but after DC3 was compacted, the temperatures diverged, which demonstrates the effectiveness of the technique. At D4, where the plot was compacted throughout the winter early, those differences in temperature persisted for the rest of the winter, even after compaction had ended. And here we have the weekly N factors, which were calculated using air temperatures from Mayo Airport and kilometer 124 of the Dempster Highway during the study period. Typical freezing N factors are between 0.1 and 0.7 in northwestern Canada, and all of the undisturbed plots fell within this range. MU3 and MU4 had an average N factor of 0.39, while MC3 and MC4 had an average N factor of 0.59 for a 0.2 increase. At the Dempster sites, the average N factor at the undisturbed plots was 0.36, and at the compacted plots, it was 0.52 for a 0.16 increase. Surprisingly, the undisturbed snowpack in Mayo had a larger N factor than the undisturbed snowpack of the Dempster Highway site, even though the density was much lower. And in general, the effects of compaction thermally were very different or very similar between sites. Both were able to replicate the effects of a thin snowpack by pushing the N factor up towards the higher end of what's found naturally. So to summarize the last 5 pages full graphs that I've shown you, here are the average values for the undisturbed and compacted plots over the duration of the winter. Snow depth was 30 centimeters lower in Mayo, as opposed to only 9 centimeters with Dempster. Hardness was 3.1 compared to 0.8, and density 156 compared to 40. In contrast, the difference in ground surface temperatures and N factors was only slightly larger at the Mayo sites. And the reason for the asterisk here beside the mean temps for Mayo is because at M3 and M4, the field sites were broken up by road widening sometime before the final field trip in April. But just looking at temperatures in March and earlier, so the first 4 months, they were about the same. So ultimately, it didn't actually make very much difference, but they're not quite the same size here. So looking at what's going on here, it's a bit difficult to compare between the sites directly, given this difference between them. But I think one key takeaway is that they're effective for different reasons in different locations. In Mayo, it was pretty straightforward. All the snow was soft and it got smushed. But at the Dempster sites, only the depth hoar layer got smushed, and this suggests that the depth hoar layer has a disproportionate influence on the thermal conductivity of the snowpack, even beyond what would be expected based on its low density. The idea that the depth hoar layer generally has low thermal conductivity is commonly accepted, but the exact extent of the thermal conductivity of the low thermal conductivity appears to have some uncertainty. In a 1992 paper, Sturm and Johnson published hundreds of thermal conductivity measurements of depth hoar and wind slab snow samples from the Arctic tundra. Their findings reported varying levels of thermal conductivity between different stages of depth hoar development based on their structure. Thermal conductivity, and this is shown in the diagram on their right. They have a nice drawing of all the different stages. Thermal conductivity generally increased with metamorphism as the snow crystals grew, right up until they reached stage 4, in which case there's a dramatic drop in thermal conductivity. At this stage, the crystals have grown large enough that they begin to spread apart, and they're only loosely connected by thin contact points. So there's not really much room for conduction. This caused the thermal conductivity to be reduced to as low as below 0.05 watts per meter Kelvin, and that was the really low thermal conductivity that was on the graph earlier in the slides. And this was even in snow with density in the range of 200 to 300 kilograms per cubic meter, so it's highly unusual. The snow was described as being held together so loosely that it broke apart at the slightest touch, and that's what was observed right at the bottom of the snow at the Dempster field sites. In Mayo, the depth hoar layer was clearly visually distinct from other layers, but its hardness and density were nearly the same, and that makes me suspect the depth hoar was at an earlier stage of metamorphism. The sites were dry, so there's less moisture available, which is bad for depth hoar, and the metamorphism appeared to be more spread out to the snowpack. And Dempster is mostly in a thin layer at the bottom, whereas in Mayo, it seemed like it was almost all the way through to a lesser extent. So the sites were unknowingly set up over a drainage ditch, so there's tons of moisture available. And I'm not familiar enough with depth hoar development to know if this is a thing, but because the snow was the wind slab snow above it was mostly impermeable, it seems to me like the water vapor was getting trapped at the bottom of the depth hoar, and that might have caused it to metamorphize into a much higher stage more quickly, because it did look much more crumbly compared to Mayo. So the difficulty with modeling thermal conductivity in tundra is not a new problem. At least as of 2019, detailed snow physics models, Crocus and Snowpack, struggled to simulate high Arctic snowpack thermal conductivity accurately. Both models simulate the snow as having high density and therefore high thermal conductivity, but field results have consistently shown the opposite, whereas the tundra snowpack has high density, but also low thermal conductivity. And that's mostly because of that basal depth-hoar layer at the bottom. The inaccurate simulation of this layer can throw model results off by up to 4 degrees. So here's some existing research into snow compaction and ground temperatures. First off, there's a paper led by Brendan O'Neill that was the biggest inspiration for my work. Here, Brendan and Chris simulated snow management, including compaction, and it found that it should be effective at reducing ground temperatures. So that was what my field experiments were intended to test. Next up, there's the experiments at Beaver Creek test site. Here, researchers from Laval University set up a test strip of road where they tried out different strategies to reduce ground temperatures, including air convective embankments, snow plowing, installing culverts, and creating a snow sunshed that blocked snow accumulation and provided shade. The snow plowing was surprisingly not very effective, but the snow shed was among the most effective treatments and showed great promise, even though it's been held back from widespread implementation since due to costs and potential safety concerns, but it shows the potential for snow management. Next up is the Tassiuak airstrip test site. They didn't mangle that too bad. Here, a variety of techniques were also tested, including heat trains, air convective embankments, and widened embankment slopes intended to limit snow accumulation. Here, over 10 years, the widened slopes outperformed the other options and caused the permafrost to grade under the shoulder by over 1 meter over 10 years, while the reference site degraded by over 3 meters. So it was extremely effective and very promising for snow management. Next up, there's the practice of yukifumi, which I found out late in the stages of my work, is the practice of compacting snow to control ground temperatures for agricultural purposes in Japan. The objective is to get deep enough seasonal frost, so that it kills weeds while leaving the other crops alive. I believe that they had potatoes in the paper I was looking at. The snow also can be completely cleared for colder ground temperatures, but the idea of compaction is that it allows for more precise control. So clearly it works. And finally, there's ski slope grooming. I found a paper talking about how groomed ski slopes experience significantly colder temperatures on average. And I found a research study that was aimed at confirming this. They measured the density, thermal conductivity, and depth of the snow. And they found that they're all significantly modified by compaction, but there wasn't actually much of a difference in ground temperatures. This was partially because air temperatures through the winter were only just below 0 degrees, so there wasn't much of a temperature gradient, not much that compacting the snow would do. And also because there is more snow constantly being piled on the ski slopes, and that partially counteracted the effects of compaction. Interestingly, it took about a month longer for the snow here to thaw compared to undisturbed snow, and I didn't watch the snow thaw at my sites, so I'm not sure what happened there, but there's a lot of potential there if it's able to shorten the thawing season. So next up, I want to talk about surface energy balance management practices just as a general concept and where snow fits in. As I discussed back on the first slide, by pushing the snow off the driving surface and onto the shoulder, maintenance workers create a surface energy imbalance that exacerbates road damage. Some form of correction is likely to be cost effective to minimize this risk, whether it be snow removal, compaction, or manipulation using snow fences. As you travel south, however, or as climate change pushes climate boundaries further north, DDF becomes smaller, and that means modifying NF becomes less effective at changing ground temperatures. So further north in areas of extensive permafrost coverage, snow management alone might be sufficient for stabilizing the permafrost, as we saw at Tassiuak Airport. As you move south into sporadic discontinuous permafrost, other treatment methods might be necessary. So the snow sunshed, for example, combining NF and NT modification was very effective. But I think really that's just scratching the surface. So for a really extreme example, at the southern limit of discontinuous permafrost, permafrosts might only be found on north-facing shaded slopes in peat bogs that are covered by thin snow cover. And if that's the case, if we're to recreate those conditions on the embankment shoulder by planting a layer of peat moss, compacting the snow during the winter, covering the shoulder with a tarp, and maybe watering the tarp on hot days, theoretically, we should be able to lower ground temperatures just as much and stabilize permafrost under an embankment that has the same air temperature. It's obviously an extreme example, and in reality, it would become ineffective well before that point. But because there are minimal structural changes to the embankment from these practices, you could simply stop treatment once climate change renders it impractical and do a controlled thaw on problem areas. I believe collaboration with experts in snow and Arctic plants could provide ideal site-specific, year-round energy balance management strategies at a given location that are able to cool the ground as effectively as engineering solutions, but for a fraction of the price and with added adaptability. And snow compaction could be another tool in that toolkit. So in conclusion, plowing snow from the driving surface creates an energy imbalance that snow compaction can minimize. Ground cooling through engineering solutions, at least as of 2009, cost between 100,000 and 500,000 per kilometer per year to implement. I know it's much higher than that, but that is what I could find a source for. And the cost difference compared to snow compaction is just so many orders of magnitude different that it doesn't really make a difference. It's all far more expensive than paying someone to just drive over the snow. And both actually had similar results based on my experiments, since I found engineering solutions typically only cool the ground by about 1 to 4 degrees Celsius. So snow compaction may offer an inexpensive, simple alternative that can provide comparable results when snow conditions are suitable. And it has the potential to stabilize extensive discontinuous permafrost on its own, but moving south into more sporadic permafrost, it would likely be insufficient. And finally, I have some acknowledgements. I just want to thank Carleton, Q Jessa, and Chris Byrne for providing extensive support throughout the whole project. Great. PermafrostNet for also providing support and collaboration and resources. Jen Humphreys, who was my research assistant and came for almost every trip and was pretty much invaluable for field studies. And Emily Stewart-Jones, who came for the last trip and also helped out a ton. First Nation of Nacho Nacton, who helped out by doing the snow compaction. They were just a blast to work with, and they traveled really far to help me out, even though the compaction itself was really quick. So I'm really grateful for that. Breeze Camels and Leif Reploth for showing me around the Dempster. It was crazy coming up there from Ottawa with no experience, so that really helped. And finally, Yukon Highways and Public Works and my contact there, Mike Scarizi, they took care of licensing, which allowed me to do the project and made things a lot easier. And that's it. That's everything.
Thank you so much, Pat, for your presentation. You have done really impressive work. Yeah, thanks for sharing your work with us.
Thank you. Thanks.
Yeah, so we have some time for Q&A, doing a quick Q&A. If anyone has question, please unmute, or you can just use the hand raise feature. So yeah, feel free to ask your question if you have any. I can't see any question.
I just have a comment. Great presentation, Pat. And it's like, what was impressive to me is that you get this temperature effect even from just a snowmobile. Because
sure, yeah.
You know, there's cross-country ski groomers that can go behind a snowmobile and like vibrate and stuff, and it would be like, it's amazing you got that temperature effect just from a, you know, relatively light snowmobile. So yeah, I thought that was pretty cool.
Yeah, and it was so easy too. Like it was a lot of work for them to come out to the field sites with me, but by the time
Yeah.
they got there, like it's like they thought I was joking at first. Like they just drove for like a minute and they were done. So yeah.
Yeah, and also good to see like the cost, like a cost comparison between, you know, like an engineering solution and this compaction. So yeah, nice work.
Yeah, yeah. Once you take out the actual embankment engineering and bringing construction materials in and hiring consultants and all that, it just costs just skyrocket. So if you're able to find solutions like this, whether it be snow management or any sort of just managing the energy balance so heat flows out of the ground naturally, I think that's always just going to be just so much more efficient.
Yeah, nice.
Yep. Please, Tim, go ahead. Yeah.
Hi, thanks very much for that interesting presentation, Pat. And I was wondering if you have chatted with Alice Wilson in Inuvik. There could be some interesting opportunities to look at your results and then the results that she's had from her snow compactions between Inuvik and Tuck. You've done, from what I can see, a really interesting job of looking at spatial variability in snow conditions and how compactions can modify temperatures. And she's had a chance to do some multi-year investigations where snow conditions have been different from one winter to the next. So there might be a neat opportunity to talk about results with her and see if you can, if your results and hers lead to even more insight on snow compaction that neither project itself would have been able to show.
Yeah, I heard she'd been working on it. And it's really interesting having another site just even further north, considering how different like just my two sites were. I haven't had a chance to speak with her too much, but I would definitely be interested to see how the results differed, especially with deeper snow depths too, because I don't think a snowmobile would work with several meters of snow depth. I was fortunate that it was like under a meter, so that changed things quite a bit, I'd say.
Thanks again. Yeah.
Thanks.
Emma.
Hey, Pat.
Hey.
Yeah, it was a great presentation. I just have one question about your site. In the right of way, the cleared section, was there a difference between the Mayo sites and the Dempster sites? Was one bigger than the other? I'm just wondering like how big of the cleared section it was.
The size of my sites were the same. They're all 50 meters by 5 meters. If they had more or less space for me to work with, I didn't know. I thought they were just the exact same size of right away. So I figured I'd just make the same dimensions to be safe and not, so I wasn't allowed to go past it.
Okay. Are you planning to do any modeling with temp W with your data?
At this point, like my thesis just has so much stuff in it that I'm like trying to cut stuff down, if anything. Like I think it'd be really useful, but I'm kind of just trying to finish up at this point. So yeah, there's not really all that much room left for it, but I think it would be really interesting though.
Okay, perfect. Thank you.
Right. I think there isn't any more question. I think we can like finish the session early, and it was really nice having you presenting your work here, Pat. Thank you so much again for participating and sharing your work, and yeah, and thank you everyone for joining us for today's presentation.
Thanks everyone.